In this part of a series of videos, we will demonstrate the implementation of the above discussed backpropagation algorithms for neural networks for training a neural network. We will use the demonstration data as we have used before. You can review the lectures, the previous lectures in this course. Basically, we load the iris data and take two attributes from each flower and convert this classification problem where in the iris you classify the flowers into three classes. For demonstration's purpose, we simplify this problem as to a binary classification problem. We take the first two classes of flowers and try to classify these two classes of flowers. So we simplify the problem by using only two attributes and do only two classification problem, which is slightly different from the previous construction, is that we will use 0 to represent one class and 1 to represent the other class. This difference is not essential. It's just a superficial way of using different samples in classes, which makes the numerical processing simpler in the construction of neural networks. So let us first, in this video, define a neural network class, which is the template of building neural network objects. Recall that we will adopt this neural network structure. Well, this is not the exact illustration in which we will use 4 instead of 2 neurons in this layer. Therefore, we will have a different number of input and output in the first layer of the neural network, which make it more clear from the programming point of view. And in the second layer, we'll take the output of the first layer as the input and generate one probability. Let us interpret this probability as the probability that this particular input sample belongs to the class 1. If you recall, we have two classes here. One is labeled as 1 and the other is labeled 0. And we will interpret this as the probability of this particular flower belongs to class 1. So let's execute the data preparation block first. Now we have the data. Let's have check. We have X train. Okay, we have 70 samples and each sample has two attributes. And let's print out the Y train. Each sample belongs to either class 0 or class 1. And the task is now to build a class of neural net to classify the two kinds of samples. To achieve this, let us prepare the useful quantities in the computation. Def initialization of the class. We take the self and let's first have a random number generator as we always use to initialize model parameters. Sorry. Random state to like this magic number. Okay. Now let's take a look at necessary quantities. I'd like to refer to this animation. So we can see we have this access input, and here we need a W matrix. I will put W here. NumPy dot No, we need the initialization. Random, we use normal distributed random numbers, which are around 0. So the W matrix has the same number of rows as the number of input variables. So we have 2 in this case, because in the X training we have 2 attributes, and as we have said, we will adopt 4 intermediate quantities here, like what is shown here. And self.u is the matrix of the second part of the second layer of neurons. So it has 4 inputs and only 1 output. I'd like to use small parameters. Okay, well, so now we have the necessary parameters defined. Let's do the forward function. Def forward solve, and let's say if we have an input of x. So we will do soft dot. No, we can write it. For example, here. We do this matrix multiplication. X and the W parameter, and now look, we need to convert those pre-activation, those values from the linear combination of the input attributes into the activation values of those first layer neurons. The activation function, for the activation function we will adopt sigmoid. Let's define the sigmoid function here. Sigmoid x. It is a sample function to define return 1 over 1 plus exponential of negative x. For let's have h is sigmoid a, and let b is dot h, and the second layer of parameters, and let's not call the output y. Instead, let's call that p to represent the prediction of y. Therefore, we will have a clearer symbol when we define the loss function. Sigmoid, sorry, p. So the p will represent the network's prediction of each sample belong to the class 1. Let's run this block of code and have a test. Let's see, n is neural net. After defining n, we will use the function of n predict forward prediction of x train, and let's just check for a sanity check. Let's look at if the prediction has the desired shape. Oh well. Excuse me, we should have self.u to refer to the parameter defined here. belonging to this particular object. It seems to be with the right shape. Of course, you may notice that this is there is a singularity in the dimension. It has 70 rows, and in each row it has one element. This is different from the Y training, which is just a vector rather than a very tall matrix. So with that, we want to squeeze it. Therefore, to make the format of the output of the neural network to be consistent with the labels, the annotation in the training data, well, let's print out these two set of values. So maybe we can take out the first 5. Now, this is a simplification of writing this way. That means to take the first 5 elements in an array. Okay. More or less as expected, we predict them as some very ambiguous value with approximately half of the chance of belonging to class 1 for every sample. That is to be expected when we haven't let the model to see the data at all. But from the point of view of matching the format, the output is expected, and the sanity check passed. In the next step, it's natural to have a comparison between the predicted value and the Y. So in the next video, we will show how to do this.